Hello everyone, and thank you for being here. Our project is titled Generating Python Code from Natural Language Instructions Using Code T5. In this presentation, we'll explain how we fine-tuned the model to translate plain English into Python code. Our goal was to explore how natural language understanding can bridge into automated coding. Let's look at the problem. On the left, you see a natural language instruction, and on the right, a piece of Python code that could be the answer. We aim to build a model that can generate this code automatically just by understanding what the user wants. Specifically, we wanted to, first, help users write code by describing it in plain English. And second, fine-tune code T5 on the Konala dataset, which contains pairs of instructions and code. Since code T5 is pre-trained, we adapted it to this task by fine-tuning it on Python code generation. Here's the full pipeline of our project. We used the Konala dataset designed for code generation. It contains 2,879 natural language code pairs, 2,379 for training, 500 for validation. Each entry is stored as a JSON object with two fields, src for the input instruction and tgt for the output code. As shown on the left, many are realistic developer questions, like those from Stack Overflow. These examples show that the model successfully learned a one-to-one mapping between a natural instruction and a Python function, which is essentially the goal of supervised learning. Before training, we focused on thoughtful data preparation. First, we aligned real-world instructions with executable Python code. The dataset wasn't artificially generated. Second, we minimized pre-processing. We didn't rephrase or filter natural language too much. Finally, instead of trying to augment or expand the data, we focused on formatting it in a way that's directly usable for training. The model we used for code generation is called Code T5 Base. This is a sequence-to-sequence transformer model. It uses an encoder-decoder setup and is trained with token-level cross-entropy loss. Pre-trained tasks included code summarization and generation. Tokenizer splits text into subwords, which is useful for code. Here's our training setup. We used a small batch size and trained for 5 epochs. The learning rate was linearly decayed, weight decay prevented overfitting. For evaluation, we used BLU score to compare model outputs and references. These are the decoding hyperparameters we used when generating Python code from the trained model. We used beam size search with size 8 to explore multiple decoding paths and pick the most likely one. In sequence generation, beam search helps the model consider multiple possible outputs, which improves the quality of the final code. A temperature of 0.7 and top P sampling at 0.9 were applied to introduce a bit of diversity while staying within a reasonable range. We also blocked repeating phrases using no repeat n-gram size 2. We evaluated the model using the BLU score, which measures how closely the generated code matches the reference. Our score was 14.48, which might sound low, but that's common in code generation tasks where even small formatting changes reduce the score. During training, the model showed smooth convergence. The training loss dropped from about 2.7 to 0.89 over 5 epochs. Before settling on the base model, we also attempted to fine-tune Code T5 large. This model has about 770 million parameters and in theory could have performed better. But in practice, we ran into two major issues. First, memory. Second, the training time exploded. We also saw gradient accumulation and checkpointing adding more latency. We then used the trained model to generate Python code from new prompts. We ran a separate evaluation on 500 validation samples. The BLU score came out to 17.7 and the completion success rate was 96.2%. This shows that the model generates synthetically valid Python code in most cases. We also analyzed the 19 cases where code generation failed to compile. Overall, code structure was solid, but logic and variable names still need refinement. After fine-tuning the model, we deployed it in two ways, locally using Flask and Docker and Hugging Face spaces. These interfaces let anyone type a natural language question and receive Python code in return, making the model practically usable. This is the web interface we built using Flask and Bootstrap. Instead of just showing model outputs in a notebook, we designed a real-time user-facing application. Users can type a natural language question immediately receive Python code as output. We also added predefined examples and copy button to make indirection smoother. While deploying with Docker, we ran into several real-world engineering issues. First, our model failed to load properly due to hidden dimension mismatch, pre-trained weights, and the model architecture. We tried using ignore mismatched sizes, but it still degraded the output quality. We also experienced memory overflow on our local machine, so we explored quantization and considered adapter tuning. Finally, we ran into port conflict on the default port 8080, which was resolved by switching to 8888. We also deployed our model to Hugging Face hub and connected it with a Gradio demo. The process involved uploading the fine-tuned model, writing a model card, and setting up a simple web interface. Anyone can now type a coding question into this interface, even without writing a single line of code, and receive Python code in return. In deploying to Hugging Face, we faced three main limitations. First, our model struggled with complex prompts like multi-step logic or unusual Python libraries. To mitigate this, we designed a fallback UI that returns predefined answers for frequent queries. Second, large model size caused high memory usage and slow interface. We are planning to explore adapter-based fine-tuning, which lets us train just a small part of the model. Finally, dimensional mismatches led to degraded outputs. As a future step, we are considering knowledge distillation and quantization to build smaller deployable models. That's all for our presentation. Thank you.